Okay. Hello, everybody. I'm Hongzheng Zhao from Peking University. So I would like to thank the organizer for giving me this opportunity to present our work. So this work was mostly done when I was still a postdoc in Dresden, together with Roderich and Moessner, Marin Bukov, and Marcus Hell. So yes, the title is Making Trotterization Adaptive and Self-Correcting, and most of the work that I presented today can be found in this two publications shown in the corner. Okay, so today my talk will just be roughly can be divided by in this a few sessions. So at the very beginning, I would just give a brief introduction to thermalization, and I know there in the audience there are lots of experts on this topic. And then I would just move on to digital quantum simulation. And especially, I would just briefly introduce trotterization as well. And then I would just move on to our algorithm, which is a trotterization, but with adaptive step sizes in order to improve the performance of digital simulation. And then I would also generalize it for time-dependent systems. And in the end, I would just summarize our result. Okay, so thermalization. So this is, it's a quite a common phenomena in our daily life. But if you think about the classical system, it's most of those equations of motions are ergodic and also nonlinear. And at long times, those classical many-body system would just tend to thermalize at long times. So here I just give a simple example. So suppose we start from this a mixture of ice and water, which is far from equilibrium, and then we just let the system evolve, and then for sufficient long time, whether in the end you get water or ice purely depends on a few thermodynamic quantities, and here it's just the temperature itself. So it's relatively straightforward. And then if we look at quantum systems, such a relaxation or equilibrium phenomena can also occur. And then, so here I just imagine if we have a closed many-body system without a bath, and they are interacting with each other, following some generic interactions. And then we also start from a non-equilibrium state with a initial polarized state, for instance, and then you just let the system evolve. And at long times, you also see this relaxation of this magnetization, and at long times, you don't really see the oscillation that you saw at early times. So this is indeed a quite puzzling phenomena, at least a few decades ago. The main reason is for classical system, you get normally a nonlinear equation of motion, but for quantum systems, the Schrödinger equation itself is linear. And if we start from a pure state, the system will always remain pure. Therefore, you can't really reach this the so-called global thermalization. But later, people gradually understand this phenomena and have this sort of the concept of local thermalization. So basically, if you only look at a small subregion of a many-body system, the rest of the system can act as its own bath, and then they can just exchange energies, also information, and this is the reason that normally currently we understand why we see this kind of relaxation process, and then at very long times, those equilibration of these local observables also. They can just be predicted by some canonical ensemble, which only depends on the temperature or of the initial state or the energy of the initial state. So you can also make it more precise by saying, okay, following some eigenstate thermalization hypothesis, we can also write down its off-diagonal or diagonal matrix of the system, and you will see that at long times, the diagonal part will just mostly contribute to this long-time relaxation. Recently, people also ask the question that how does this far from equilibrium system approach this long-time equilibration? And this is, at extremely long times, you can simply use or develop some perturbation theory or use some numerical simulation, for instance, exact diagonalization or TBD method, just so you can simulate it and understand its initial time evolution fairly well. However, we also care about the transient dynamics, which is much more complicated. But those transient dynamics, they will highly depend on the model itself and also the way that you couple them and dimensionality, initial state, and so on and so forth. But those transient dynamics actually are very interesting because if you want to understand, for instance, the low energy excitation of a piece of material, or if you want to study, if you have conservation laws, you want to understand how does transport happen or how does hydrodynamics emerges from this many-body system, or you want to study how does the correlation function spread or entanglement grows in time, you have to understand this transient dynamics. And in the previous days, there are lots of interesting talks towards this direction. For instance, people can construct some solvable models. For instance, if you have integrable systems, or here you can also have dual unitary circuits or generalized ones. But to be honest, I mean, those systems are, for most generic systems, you do not have those very special structure. And then, so for me, I'm quite interested in the idea about using quantum simulation to study this transient dynamics. Yeah, so for instance, if you can build up a quantum computer or a quantum simulator, just to time evolve your system, and then in order to understand this thermalization process. There are also many different ways that one can do quantum simulation. For instance, you can do analog ones. You create the code atoms and you spread it in the optical lattices, and you let them interact, contact, and evolve in time. But today, my main focus would be the digital ones. So suppose you have a quantum computer. We do have a few noisy ones, but not as good as we wish. But still, we can imagine we have those, and then the idea is basically I want to use the gates to time evolve a quantum system. And those systems, for simplicity, I would just start from a time-independent Hamiltonian, so which is just a sum over a few local terms. And one of the key important thing is for those static systems, the energy is conserved, which is indeed a key element for our algorithm that I will introduce later. So the general idea for this digital quantum simulation is that we do not have direct access to this many-body Hamiltonian. Okay, so therefore, this global time evolution unitaries, U itself, is not accessible. So normally, what people do is we can decompose this global object to a product of more elementary local quantum gates. So here, just in this pictures, what I'm showing is this black circles just represent the state or the qubits, and then you can decompose your target unitary into this product of single body rotation or this two body gates. Okay, and this decomposition is actually very precise if the step size delta t is relatively small. And sorry about it. And if you want to reach a relatively longer time, for instance, a fixed time t, you just repeat this process. You do it layer by layer, and then you just get a long time evolution. So if you can also treat this from another perspective. You can say, okay, I basically design a numerical solver, by using this Trotterization algorithm. And this numerical solver solves this shorting equations on quantum computers, but at a fixed step size, delta t. Just as many other approximation method, this Trotter decomposition is also approximate, which means you do have errors. And normally we call this Trotter error, and this is indeed a very active field that people try to understand what is optimal decomposition of this target unitary, and how does Choudhury error scale versus the step size delta t. So as you can see, normally you can actually systematically suppress your Choudhury error just by using a relatively smaller Choudhury step size. But it actually introduces the computational resources in order to reach a fixed time for your simulation task. So this is indeed not only a problem for quantum systems, but if you think about many classical algorithms that you want to solve your dynamics in classical systems, you also have this issue, but people have spent decades on this and try to reduce the computational time. For instance, just by using adaptive solvers. And the idea is actually very simple. So imagine that you have a complicated dynamics, and errors will also not happen uniformly in time. Therefore, you can always track the errors along the dynamics. So when this error is large, you simply reduce your step size, okay, to keep this error overall bounded. But if you have this error, you check this error and notice, okay, this is relatively a small error. I can enlarge my step size in order to save my computational time. So the famous example is just Ruggie-Kuta method. So here I also show a dynamics of three particles, which I just downloaded from Wikipedia. So there, three particles are attracting each other by gravitational forces, and you can notice that when two particles are close to each other, where their forces is very strong, therefore the error actually happens rapidly, and computationally the time actually takes longer. But if those two particles are far away from each other, you can increase your step size to speed up your simulation. But now, if you think about the current NISQ or quantum computers with extra noises, the limited computational resource is not really the computational time, but actually the gate number that you will use in order to implement your target simulation. Or equivalently, you can say this is the limitation is a circuit depth. But for those who are not familiar with the current, the quality of these quantum computer simulations, so here I just give you an example. So this is an example that Adam Smith and also co-authors performed in a few years ago. So they just studied the quench dynamics from a polarized state in a 1D spin chain, and you can easily simulate this dynamics classically. And if you do Trotterization, you get this grid dots, okay? And then if you run the same algorithm on quantum computers, this green one's actually the one you got from this quantum computer. So you see that even at very early times, you cannot even complete the first oscillatory behavior before your signals completely die. But then over the recent years, we saw so many news from Google, from IBM, that they reach higher and higher gate fidelity, and we also know that you can develop many error mitigation methods to just reduce this errors. But we have to admit that we are still far from fault-tolerant quantum computing. Therefore, minimization of the circuit depths rather than this physical runtime is indeed the current central optimization task for digital quantum simulation. So here, this actually motivates our research. So basically, we want to ask, is it possible that we design a Trotterization algorithm with adaptive step sizes? This is very, it's kind of motivated from classical ones, but then is it possible on quantum computer as well? But we just realized that it's not a simple task, and then there are mainly two challenges in solving this problem. So the first one is, what kind of measurable physical quantities should we use as errors to adapt our step sizes? So if you think about classical numerical solvers, you always have your solutions for your classical equation of motion. And for Ragi-Kuta type of method, you simply do, compare your simulation with one step to a simulation with two different steps. And you know that the more step size you use, in principle, you get better solutions. And then basically you can compare these two solutions and decide what is the suitable steps in the future simulation. Yeah, but then this is almost impossible for a quantum computer for many body systems, especially in the thermodynamic limit, because it's impossible or exponentially difficult if you want to get the precise information of your wave functions. Therefore, it's almost impossible that you can directly compare the difference between two wave functions. So we need to find in order to do this, we need to find the measurable physical quantity as errors. And then the second challenge is, whenever you discretize time, you actually violate the energy conservation of your target system. So for now, we think about time-independent systems. So at the very beginning, I highlight that it has energy conservation. But if you think about, when you do Trotterization, you explicitly introduce time dependence. And people in the talks of during this seminar, people study Floquet dynamics, and you know that energy is no more conserved, and you have extra problems like heating. And this is a similar thing here. But for Floquet or Trotterization with a fixed step size, this is okay, because you can always have some quasi-conservation loss of energy itself. But if now you think about Trotterization with adaptive step size, you actually don't have this discrete time translation symmetry, and naively you would just believe that it will causes more heating problem and destabilize your algorithm. But we basically propose a feedback loop to solve these two challenges, which ensures the conservation law of the target Hamiltonian approximately. And the key error that we figure out that you must control is the energy and the energy variance of a many-body system. So how can we do this? So the algorithm is the following. So I give you a quantum state, and then you can just choose your favorite Trotterization decomposition. And then I say, I use a relatively larger step size, and I time evolve my system. And now I can perform measurement. So, you measure, you collapse, but you can still repeat this process. You can get a good statistics of these conserved quantities. So here it's only energy and energy variance, and I do not assume if you have other conservation laws, you also need to put it here. And now, crucially, you know the answer of these conservation laws, because you can simply determine them from your initial state. And then you can compare, after you do this time evolution, are the errors in the conservation laws bounded, depending on your on the threshold value that you preset, are these errors bounded? If yes, you propagate your state. If not, you need to propose a new smaller step size until this conservation laws are relatively well preserved. So this is just the simple feedback loop that we design. And in the following, I would just show you some numerical simulation to show it works. So currently, I do not have a quantum computer, so I just run all of the simulations on my laptop. So here we just we consider a 1D spin model, which is non-integrable. So it involves two different pieces. So one involves all the terms in z direction. So it's Ising interaction plus the z field, and I also have an x field. Okay. So now I choose a Trotter decomposition with a second order Suzuki Trotter, but it doesn't really matter which one you choose. And now I just try to run the simulation. So first, I will run exact diagonalization starting from a polarized state in y direction. So this is far from equilibrium. And then I will measure the magnetization in x direction. So this blue line, for the black lines, they are exact solutions. So you can see that the dynamics is very rich. So at the early times, you see very coherent oscillations, and at intermediate times, you slowly relax, and at very long times, you completely relax, reaching the prediction by this eigenstate thermalization hypothesis. And then I just run this adaptive Trotterization method, which is this orange dots. For this specific simulation, you can realize that this adaptive method not only captures the early time coherent oscillation, but also the intermediate transient dynamics and also the long time evolution. And you do see some errors, for sure, but those errors can be systematically suppressed or controlled by using a smaller threshold values in our conservation laws. And this insight just shows the step size, which is automatically chosen by this adaptive algorithm. And you can see that at early times, actually, it does what we wish, right? So it automatically picks relatively smaller step size in order to control this error. But at long times, your system gradually thermalizes, and you do not care about Trotter error, not as sensitive as the initial state to Trotter errors. Therefore, you can just gradually enlarge your step size. But there are also fluctuations in the middle. But it actually highly depends on the model, on the state, and also on the time. So here I also compare this results with a simulation without explicit constraints in energy variance. So this blue lines only preserve energy fairly well, and you can see at extremely short times it's okay, but just after a very short time, you see significantly deviation from the correct answer. Therefore, I want to highlight that bounding deviations in energy variance is actually very crucial to realize a stable digital simulation. But here, I just want to mention one technical point, which is when we want to search for a proper suitable step size, this process can actually also be very efficient. We do not need very complicated classical optimization algorithm. We just do a few trials. So here it's like 5 or even less trials of step sizes, and then we can just determine what is step sizes, what is a suitable step size to propagate the state. Okay, so here I just compare our simulation results with this, conventional fixed step Trotterization method. So there are many different ways that you can benchmark your algorithm, but here I want to reach the same simulation time, and I fix the total number of unitaries that you are allowed to use, and then I run the simulation. So again, these black lines are exact solutions, and then the orange dots are adaptive Trotterization method, and you can see they closely follow the exact solution. But if you just use a fixed step Trotterization method, you see even for the first step, you see a huge error in local observables, and this error can never be corrected back to the exact solution. We further not only look at the local observables, we also check the behavior in the energy. And you can see that, so the energy itself, the black line, is a conserved quantity for the target system. But if you run our adaptive method, you actually realize that those orange dots are oscillating around the correct value of this energy, which means this algorithm, just by simply changing or adapting the step size, it can self-correct errors in energies. This energy errors actually does not accumulate in time. But if you look at the energy obtained by using fixed step Trotter, at early times, you see clear deviation, and at later times, you reaches this quasi-conservation law of energy, but it significantly deviates from the exact solution, and it cannot be corrected back to the correct energy manifold. So this is actually a very important feature of our adaptive algorithm. And then this is actually a natural question to ask, right? So why we only need to control the lowest two moments of the target Hamiltonian? Why don't we worry about higher moments? Yeah, because for target system, all higher moments should be conserved quantity, just as shown in these two figures, where I computed the third and the 10th moments of the system, and you see the black lines always remain conserved. But then if you let's say do only control energy conservation law, you get this red dashed lines and you see clear deviations. But now if you add the constraints on energy variance, again, you get this orange dots and you see that automatically higher moments are much better preserved. You do not need to explicitly introduce the constraints in the algorithm because measuring those higher moments are actually very expensive on real quantum devices. But here you don't actually need to do so just because constraining the energy variance itself is enough. So we can't really, prove this rigorously, but we can provide a heuristic answer to this behavior. And the idea is, according to central limit theorem, the correct characterization of the energy distribution only requires the first two moments of your target Hamiltonian. You do not need to worry too much about the higher moments. And this is, you can suddenly say, okay, what if I prepare a cat state in the energy space? And for sure, this is far from any central limit theorem, but those states are also really hard preparable on any quantum devices. But for the most easy access ones, for instance, product states, actually there exists a rigorous proof for this energy distribution, by Michael Hartmann and others, and they give actually mathematically, you can show that the energy distribution approaches the Gaussian distribution in the thermodynamic limit. So this is actually the key ingredient for our algorithm to work. It highly depends on we believe the system obeys statistical physics, therefore it works fairly well, and you do not need to measure these higher moments, or you do not need to measure directly the wave functions of your quantum many-body system. Okay, so there's another important feature which cannot be obtained for fixed step Trotterization method, which is the control of asymptotic errors in local observables. So based on the eigenstate thermalization hypothesis, we know that at long times we can predict the correct local expectation value just based on the energy. But now our energy have an error, based on the tolerance that we set. And then you can just do Taylor expansion. You can estimate these errors, and you can also compare the deviation between our results and the predicted value as a function of the tolerances in energy. And you can see that for sufficiently large system size, our long time error in local observables actually becomes zero if the energy tolerance is very small. And similarly, you can also study the contribution of errors from the energy variance. And although that I show you that controlling energy variance errors is very important for the transient dynamics, but at long times when the system fully equilibrates, it only contributes as a finite size effect at long times. And you can also easily verify this numerically. Okay, this actually completes the story for our first work on the if you only care about simulating a time-independent Hamiltonian dynamics. But now, if we think about more generally, if you want to study a time-dependent system, yeah, your Hamiltonian is modulating in time. What should we do? Is it still possible to change your step size? And so here in this plot, I just plot the expectation value of the instantaneous Hamiltonian h of t, and for sure it's not a conserved quantity anymore. But then the question is, in order to slightly modify our algorithm, what is the conservation law? Yeah, what should we preserve? In order to decide the error in our system. So the idea that we provide one solution to this, and the idea is, again, you can actually discretize the time into small pieces, and you can construct the so-called instantaneous conservation laws perturbatively based on Magnus expansion. And if the discretization of time is relatively small, this construction is actually very accurate. And then you can basically say, okay, for a smaller step size, I know the expectation value of this instantaneous conservation law should remain preserved, but now I can do charterize the dynamics, and then I get the error, and then I can basically bound the errors in this instantaneous conservation laws. Yeah, so this is kind of straightforward generalization of our algorithm. But suddenly we realize there is a huge problem, because if you do this, you only bound the so-called time local constraint at a given time, because you don't really know the exact solution of conservation laws throughout the whole dynamics. You actually see that at later times, the solution of your algorithm actually keep deviating from the correct results. And this is actually entropically feasible, because simply in order to satisfy the constraints, there are much more choices that actually drag you away from the correct energy manifold than the ones that can correct errors. But in order to increase the stability of this algorithm, we propose the concept that rather than use time local constraint, you need to actually control the accumulated errors throughout all of their previous simulation history, and you sum them over, and then you control these errors. And so here just is a schematic, but now I can also show you a numerical simulation. And basically with the global constraints in errors, you can actually get a much stable simulation result, even at relatively longer times. So I would also like to point out that Tatsuhiko Ikeda and also co-authors, they propose another different approach from others. They can also adapt their step sizes to solve this time-dependent trotterization problem. Okay, so in the end, I would like just to briefly summarize my presentation. So here I just gave you an example that about a adaptive and also self-correcting algorithm with controllable errors in energy and energy variance. Yeah, so the energy variance is surprisingly crucial for this purpose, and it's particularly useful if you have different time scales throughout your time evolution. So if your dynamics is always oscillating, it's kind of meaningless to use our algorithm. But as we know, for generic time evolution, you normally have different temporal behavior. Therefore, our algorithm should be perform better than conventional methods. And there are also a few open questions. So the obvious one is, what if statistics somehow fails or thermalization does not happen? How can we do? Like, what if you have a many-body localized system? Is our method still suitable to adapt the step size? Or is it possible to involve some classical optimization procedure to improve the efficiency of our algorithm? Or is it possible to generalize it to open quantum systems? Or more generally, whenever charterization is involved, for instance, even classical or numerical methods like TEBD method, you can always think about, is it possible to adapt the step size to improve the efficiency of the algorithm? And okay, so in the early end, we have open positions in China, in Peking University, and if you have good students or postdocs that they are interested in doing research in China, just contact me. Okay, thanks a lot.
Hi, nice talk. What is the initial condition you used?
So in the current simulation, I just use a fully polarized state in certain directions. So I just want to make sure it has dynamics. Yeah, but in principle, to make sure our algorithm works, you just actually any physical state. Yeah, so it should work because most of the states should have a Gaussian type distribution in energy space, unless you're you are very close to the ground state or the edge of the many-body spectrum. You may get a different distribution, but overall, it's it doesn't really have limitations on initial states,
including inhomogeneous states.
I would say so, yes, but I do not do a systematic benchmark on this. Even for inhomogeneous state, the energy distribution should also follow a Gaussian distribution in most of the cases. Yeah.
Thank you.
Any other question? Okay, so then let's thank for this very nice talk.
Thank you.
Thank you.